Good morning all students. Welcome to the next lecture of Power Generation Techniques. I am Poonam Diwan, Assistant Professor in the Department of Mechanical Engineering, Vishwavidyalaya Engineering College, Ambikapur. The topic of today's lecture is Boiler Efficiency Calculations. Throughout the lecture, we will go through the following contents: Introduction, purpose of the performance test, methods of calculations of boiler efficiency, direct method, advantages of direct method, disadvantages of direct method, indirect method. Introduction. Performance of the boiler like efficiency and evaporation ratio reduces with time due to poor combustion, heat transfer, fouling and poor operation maintenance. Deterioration of fuel quality and water quality also leads to poor performance of boiler. Efficiency testing help us to find out how far the boiler efficiency drifts away from the best efficiency. Boiler efficiency equals to heat output per heat input into 100. Heat in steam output in kilocalorie divided by heat in fuel input kilocalorie into 100. Evaporation ratio is also calculated as quantity of steam generation per quantity of fuel consumption. Methods of calculation of boiler efficiency. Basically, boiler efficiency can be tested by the following methods. First one is the direct method, where the energy gain of the working fluid, water and steam is compared with the energy content of the boiler fuel. Second one is the indirect method, where the efficiency is the difference between the losses and the energy input. Now, we will see these methods one by one. The direct method testing. This is also known as input output method due to the fact that it needs only the useful output and the heat input for evaluating the efficiency. The efficiency can be evaluated using the formula boiler efficiency heat output per heat input into 100. Indirect method, well known as losses methods, where the efficiency is the difference between the losses and the energy input. Generally adopted by the staff, accuracy can be higher than direct method. Losses can be accounted for, gives a clue for improvement area. Both these methods are suitably stated in the efficiency standard. Now, we will see the measurements required for direct method testing. Here, both heat input and heat output must be measured. The measurement of heat input requires knowledge of the calorific value of the fuel and its flow rate in terms of mass or volume. According to the nature of the fuel, for gaseous fuel, a gas meter of the approved type can be used and the measured volumes should be corrected for temperature and pressure. A sample of gas can be collected for calorific value determination, but it is usually accepted to use the calorific value declared by the gas suppliers. For liquid fuel, heavy fuel oil is very viscous and this property varies sharply with temperature. The meter, which is usually installed on the combustion appliance, should be regarded as a rough indicator only, and for test purposes a meter calibrated for the particular oil is to be used and over a realistic range of temperature should be installed. Even better is the use of an accurately calibrated day tank. For solid fuel, the accurate measurement of the flow of coal or other solid fuel is very difficult. The measurement must be based on mass, which means that bulky apparatus must be set up on the boiler house floor. Samples must be taken and bagged throughout the test. The bag sealed and sent to a laboratory for analysis and calorific value determination. In some more recent boiler houses, the problem has been alleviated by mounting the hoppers over the boilers on calibrated load cells, but these are yet uncommon. Heat output. There are several methods which can be used for measuring heat output. With steam boilers and installed steam meter can be used to measure flow rate. but this must be corrected for temperature and pressure. In earlier years, this approach was not favored due to the change in accuracy of orifice or venturi meters with flow rate. It is now more viable with modern flow meters of the variable orifice or vortex shedding types. In case of boilers with intermittent blowdown, blowdown should be avoided during the trial period. In case of boilers with continuous blowdown, the heat loss due to blowdown should be calculated and added to the heat in steam. Let us take an example. If question asked, find out the efficiency of the boiler by direct method with the data given below. Coal fired is the type of boiler, quantity of steam generated is 8 TPH, steam pressure gauge per temperature is 10 kg per centimeter square per 180 degree Celsius, enthalpy of steam dry and saturated at 10 kg per centimeter square is 665 kilocalorie per kg. Quantity of coal consumed is 1.6 TPH, feed water temperature is 85 degree Celsius, GCV of coal is 4000 kilocalorie per kg, pressure is 665 kilocalorie per kg saturated, enthalpy of feed water is 85 kilocalorie per kg. Now, boiler efficiency eta is steam flow rate into steam enthalpy minus feed water enthalpy into 100 divided by fuel firing rate into gross calorific value. When we substitute all the values, we will get 72.5%. Evaporation ratio is 8 ton per steam per 1.6 tons of coal, that is 5. It should be noted that boiler may not generate 100% saturated dry steam and there be some amount of wetness in the steam. Advantages of direct method: plant people can evaluate quickly the efficiency of boilers, requires few parameters for computation, needs few instruments for monitoring. Disadvantages of direct method: does not give clues to the operator as to why efficiency of system is lower, does not calculate various losses accountable for various efficiency level. Indirect method: indirect method is also called as heat loss method. The efficiency can be arrived at by subtracting the heat loss fractions from 100. The principal losses that occur in a boiler are L1 loss due to dry flue gases, L2 loss due to hydrogen in fuel, L3 loss due to moisture in fuel, L4 loss due to moisture in air, L5 loss due to carbon monoxide, L6 loss due to surface radiation, convection and other unaccounted losses which are insignificant and are difficult to measure, L7 unburnt losses in fry ash, L8 unburnt losses in bottom ash. Now, boiler efficiency by indirect method is equals to 100 minus L1 plus L2 plus L3 plus L4 plus L5 plus L6 plus L7 plus L8. Measurements required for performance assessment testing. The following parameters need to be measured as applicable for the computation of boiler efficiency and performance. A. Flue gas analysis like percentage of CO2 and O2 in flue gas, percentage of carbon monoxide in flue gas, temperature of flue gas. B. Flow meter measurements for fuel, steam, feed water, condensate water, combustion air. C. Temperature measurements for flue gas, steam, makeup water, condensate return, combustion air, fuel, boiler feed water. Pressure measurements for steam, fuel, combustion air, both primary and secondary. Draft. And the last one is water condition, which consists total dissolved solid TDS, pH, blow down rate and quantity. Now, test conditions and precautions for indirect method testing. The efficiency test does not account for standby losses. Efficiency test is to be carried out when the boiler is operating under a steady load. Therefore, the combustion efficiency test does not reveal standby losses which occur between firing intervals. Blow down loss, the amount of energy wasted by blow down varies over a wide range. Soot blower steam. The amount of steam used by soot blowers is variable that depends on the type of fuel. Auxiliary equipment energy consumption. The combustion efficiency test does not account for the energy usage by auxiliary equipments such as burners, fans and pumps. Preparation and preconditions for testing. Burn the specified fuels at the required rate. Do the test while the boiler is under steady load. Avoid testing during warming up of boilers from a cold condition. Obtain the charts tables for the additional data. Determination of general method of operation, sampling and analysis of fuel and ash. Ensure the accuracy of fuel and ash analysis in the laboratory. Check the type of blow down and method of measurements. Ensure proper operation of all instruments. Check for any air infiltration in the combustion zone. C. Flue gas sampling location. It is suggested that the exit duct of the boiler be probed and reversed to find the location of the zone to maximum temperature. This is likely to coincide with the zone of maximum gas flow and is therefore a good sampling point for both temperature and gas analysis. D. Options of flue gas analysis like check the oxygen test with the carbon dioxide test, carbon monoxide test. E. Planning for the testing. The testing is to be conducted for a duration of 4 to 8 hours in a normal production day. Advanced planning is essential for the resource arrangement of manpower, fuel, water and instrument check, etc., and the same to be communicated to the boiler supervisor and production department. Sufficient quantity of fuel stock and water storage required for the test duration should be arranged so that a test is not disrupted due to non-availability of fuel and water. Necessary sampling point and instruments are to be made available with working condition. Lab analysis should be carried out for fuel, flue gas and water in coordination with lab personnel. The steam table, psychometric chart calculator are to be arranged for computation of boiler efficiency. Boiler efficiency by indirect method. Calculation procedure and formula. Conversion formula for proximate analysis to ultimate analysis. Percentage of carbon is 0.97 C plus 0.7 Vm plus 0.1 A minus M 0.6 minus 0.01 M, where C is the percentage of fixed carbon, A is the percentage of ash, Vm is percentage of volatile matter, M is percentage of moisture. Formulas to calculate the combustion rate. Theoretical air required for combustion is 11.6 into C plus 34.8 into H2 minus O2 by 8 plus 4.35 into S divided by 100 kg per kg of fuel from fuel analysis, where C, H2, O2 and S stands for the percentage of carbon, hydrogen, oxygen and sulfur present in the fuel. B. Percentage excess air supplied, EA, O2 percentage minus O2 percentage divided by 21 minus O2 percentage into 100 from flue gas analysis. Normally, if O2 measurement is not available, use CO2 measurement. 7900 into CO2 percent theoretical minus CO2 percent analysis divided by CO2 percent analysis into 100 minus CO2 percent theoretical from flue gas analysis, where CO2 percent T is theoretical CO2, CO2 percent A is actual CO2 percent measured in flue gas. CO2 percent T can be calculated as moles of C per moles of N2 plus moles of C. Moles of N2 is weight of N2 in theoretical air divided by molecular weight of N2 plus weight of N2 in fuel divided by molecular weight of N2. Now, moles of C is weight of C in fuel divided by molecular weight of C. Actual mass of air supplied per kg of fuel AAS is 1 plus EA divided by 100 into theoretical air. The various losses associated with the operation of the boiler are heat loss due to dry flue gas. This is the greatest boiler loss and can be calculated with the following formula. L1 is m into Cp into Tf minus Ta divided by Gcv of fuel into 100, where L1 is percentage of heat loss due to dry flue gas, m is mass of dry flue gas in kg per kg of fuel. Combustion products from fuel is CO2 plus SO2 plus nitrogen in fuel plus nitrogen in the actual mass of air supplied plus O2 in flue gas. H2O or water vapor in the flue gas should not be considered. Cp is specific heat of flue gas in kilocalorie per kg degree Celsius. Tf is flue gas temperature in degree Celsius. Ta is ambient temperature in degree Celsius. Note: for quick and simple calculation of boiler efficiency, use the following. A. Simple method can be used for determining the dry flue gas loss. Percentage heat loss due to dry flue gas is m into Cp into Tf minus Ta divided by Gcv into fuel of fuel into 100. Total mass of flue gas per kg of fuel equals to mass of actual air supplied per kg of fuel plus 1 kg of fuel. Note 2. Water vapor is produced from hydrogen in fuel, moisture present in fuel and air during the combustion. The losses due to these components have not been included in the dry flue gas loss since they are separately calculated as a wet flue gas loss. Second, heat loss due to evaporation of water formed due to H2 in fuel percent. The combustion of hydrogen causes a heat loss because the product of combustion is water. This water is converted to steam and this carries away heat in the form of its latent heat. L2 equals to 9 into H2 plus into 584 plus Cp into Tf minus Ta divided by Gcv of fuel into 100, where H2 is kg of hydrogen present in fuel on 1 kg basis. Cp is specific heat of superheated steam in kilocalorie per kg degree Celsius. Tf is flue gas temperature in degree Celsius. Ta is ambient temperature in degree Celsius. 584 is latent heat corresponding to partial pressure of water vapor. Third, heat loss due to moisture present in fuel. Moisture entering the boiler with the fuel leaves as a superheated vapor. This moisture loss is made up of the sensible heat to bring the moisture to boiling point, the latent heat of evaporation of the moisture and the superheat required to bring this steam to the temperature of the exhaust gas. This loss can be calculated with the following formula. L3 equals to m into 584 plus Cp into Tf minus Ta divided by Gcv of fuel into 100, where m is the kg moisture in fuel on 1 kg basis. Cp is again specific heat of superheated steam in kilocalorie per kg degree Celsius. Tf is flue gases temperature in degree Celsius. Ta is ambient temperature in degree Celsius. 584 is latent heat corresponding to partial pressure of water vapor. Fourth one is heat loss due to moisture present in air. Vapor in the form of humidity in the incoming air is superheated as it passes through the boiler. Since this heat passes up the stack, it must be included as a boiler loss. To relate this loss to the mass of coal burnt, the moisture content of the combustion air and the amount of air supplied per unit mass of coal burnt must be known. L4 equals to AAS into humidity factor into Cp into Tf minus Ta divided by Gcv of fuel into 100, where AAS is the actual mass of air supplied per kg of fuel, humidity factor is kg of water divided by kg of dry air, Cp is specific heat of superheated steam in kilocalorie per kg degree Celsius. Tf is flue gas temperature, Ta is ambient temperature. Fifth one, heat loss due to incomplete combustion. Products formed by incomplete combustion could be mixed with oxygen and burned again with a further release of energy. Such products include carbon monoxide, H2 and various hydrocarbons and are generally found in the flue gas of the boiler. Carbon monoxide is the only gas whose concentration can be determined conveniently in a boiler plant test. L5 equals to percentage of CO into C divided by percentage of CO into percentage of carbon dioxide into 5744 divided by GCV of fuel into 100. L5 is the percentage heat loss due to partial conversion of C to CO. CO is volume of CO in flue gas leaving economizer. CO2 is actual volume of CO2 in flue gas. C is the carbon content kg per kg of fuel, or when CO is obtained in ppm during the flue gas analysis, CO formation MCO equals to CO in ppm into 10 to power minus 6 into mf into 28. mf is the fuel consumption in kg per hour. L5 equals to MCO into 5744. Sixth one, heat loss due to radiation and convection. The other heat losses from a boiler consist of the loss of heat by radiation and convection from the boiler casting into the surrounding boiler house. Normally, surface loss and other unaccounted losses is assumed based on the type and size of the boiler as given below. For industrial fire tube per packaged boiler equals to 1.5 to 2.5%. For industrial water tube boiler equals to 2 to 3%. For power station boiler 0.4 to 1%. However, it can be calculated if the surface area of boiler and its surface temperature are known for using this equation. L6 equals to 0.548 into Ts per 55.55 into 4 minus Ta divided by 55.55 into 4 plus 1.957 into Ts minus Ta into 1.25 per square root of 196.85 into Vm plus 68.9 divided by 68.9, where L6 is the radiation loss in watt per meter square, Vm is the wind velocity in meter per second, Ts is surface temperature Kelvin, Ta is ambient temperature Kelvin. Heat loss due to unburned carbon in fly ash and bottom ash. Small amounts of carbon will be left in the ash and this constitutes a loss of potential heat in the fuel. To assess these heat losses, samples of ash must be analyzed for carbon content. The quantity of ash produced per unit of fuel must be known. 7. Heat loss due to unburned in fly ash. L7 equals to total ash collected per kg of fuel burned into GCV of fly ash into 100 divided by GCV of fuel. L8 is heat loss due to unburnt in bottom ash percentage. L8 equals to total ash collected per kg of fuel burnt into GCV of fly ash into 100 divided by GCV of fuel. Heat balance. Having established the magnitude of all the losses mentioned above, a simple heat balance would give the efficiency of the boiler. The efficiency is the difference between the energy input to the boiler and the heat losses calculated. After all calculations we prepare the boiler heat balance where we substitute all the calculated values as shown in the chart here. In this chart, we will enter heat input of fuel, various heat losses in boiler like dry flue gas loss, loss due to hydrogen in fuel, loss due to moisture in fuel, loss due to moisture in air, partial combustion of C to CO, surface heat losses, loss due to unburnt in fly ash, loss due to unburnt in bottom ash. At last, boiler efficiency will be calculated as 100 minus 1, 2, 3, 4, 5, 6, 7, 8. Example of boiler efficiency calculation. The question is, find out the boiler efficiency by indirect method. The following are the data collected for a boiler using coal as the fuel. For coal fired boiler, fuel firing rate is 5599.17 kg per hour. Steam generation rate is 21937.5 kg per hour. Steam pressure is 43 kg per centimeter square. Steam temperature is 377 degrees Celsius. Feed water temperature is 96 degrees Celsius. CO2 in flue gas equals to 14%. CO in flue gas is 0.55. Average flue gas temperature is 190 degrees Celsius. Ambient temperature is 31 degrees Celsius. Humidity in ambient temperature is 0.0204 kg per kg dry air. Surface temperature of boiler is 70 degrees Celsius. Wind velocity around the boiler is 3.5 meter per second. Total surface area of boiler is 90 meter square. GCV of bottom ash is 800 kilocalorie per kg. GCV of fly ash is 452.5 kilocalorie per kg. Ratio of bottom ash to fly ash is 90:10. Fuel analysis in percentage. Ash contained in fuel is 8.63. Moisture in coal is 31.6. Carbon content is 41.65. Hydrogen content is 2.0413. Nitrogen content is 1.6. Oxygen content is 14.48. GCV of coal is 3501 kilocalorie per kg. Boiler efficiency by indirect method. Step 1. Find theoretical air requirement. Theoretical air required for complete combustion is 11.6 into C plus 34.8 into H2 minus O2 by 8 plus 4.35 into S divided by 100 kg per kg of coal equals to 11.6 into 41.65 plus 34.8 into 2.0413 minus 14.48 divided by 8 plus 4.35 into 100 divided by 100 equals to 4.91 kg per kg of coal. Step 2. Find theoretical CO2 percent. CO2 percent at theoretical condition is moles of C divided by moles of N2 plus moles of C, where moles of N2 equals to weight of N2 in theoretical air divided by molecular weight of N2 plus weight of N2 in fuel divided by molecular weight of N2. Moles of N2 equals to 0.1356, where moles of C equals to 0.4165 divided by 12 equals to 0.0347. CO2 theoretical equals to 0.30347 divided by 0.1332 plus 0.0347. CO2 theoretical comes 20.37%. Step 3. To find excess air supplied, actual CO2 measured in flue gas equals to 14%. It can be calculated as excess air supplied EA equals to 7900 into CO2 percent theoretical minus CO2 percent actual divided by CO2 actual into 100 minus CO2 percent theoretical, which comes 45.17%. Step 4. To find actual mass of air supplied, actual mass of air supplied is 1 plus EA divided by 100 into theoretical air, which is 1 plus 45.17 divided by 100 into 4.9, which comes 7.13 kg per kg of coal. Step 5. To find actual mass of dry flue gas, mass of dry flue gas is mass of CO2 plus mass of N2 content in the fuel plus mass of N2 in the combustion air supplied plus mass of oxygen in flue gas. Mass of dry flue gas equals to 0.4165 into 44 divided by 12 plus 0.016 plus 7.13 into 77 divided by 100 plus 7.13 minus 4.91 into 23 divided by 100, which is 7.54 kg per kg of coal. Step 6. To find all the losses. First, percent heat loss in dry flue gas L1 is 7.88%. Second, percent heat loss due to formation of water from H2 in fuel L2, while substituting we will get 3.441%. Step 3, percent heat loss due to moisture in fuel L3, which is 5.91%. Fourth, percent heat loss due to moisture in air L4 is 0.29%. Fifth, percent heat loss due to partial conversion of C to CO L5, which is 2.58%. Sixth, heat loss due to radiation and convection L6 comes 544.64 kilocalorie per meter square. Total radiation and convection loss per hour is 544.64 into 90, which is 49017.6 kilocalorie. Percent radiation and convection loss is 49017.6 into 100 divided by 3501 into 5599.17. L6 is 0.25%. Seventh one, percent heat loss due to unburnt in fly ash. Percent ash in coal is 8.63. Ratio of bottom ash to fly ash equals to 90:10. GCV of fly ash is 452.5 kilocalorie per kg. Amount of fly ash in 1 kg of coal is 0.1 into 0.0863, which is 0.00863 kg. Heat loss in fly ash is 0.00863 into 452.5, which is 3.905 kilocalorie per kg of coal. Percent heat loss in fly ash is 3.905 into 100 divided by 3501. L7 0.11%. Eighth, percent heat loss due to unburnt in bottom ash. GCV of bottom ash is 800 kilocalorie per kg. Amount of bottom ash in 1 kg of coal is 0.9 into 0.0863, which is 0.077 kg. Heat loss in bottom ash is 0.077 into 800, which is 62.1376 kilocalorie per kg of coal. Percent heat loss in bottom ash is 62.136 into 100 divided by 3501. L8 is 1.77%. Now, boiler efficiency by indirect method is 100 minus all the losses we have calculated, that is 77.77%. Now, we prepare the summary for heat balance for coal fired boiler. Heat input of fuel is 3501, dry flue gas loss L1 is 275.88, percentage is 7.88, loss due to hydrogen in fuel 120.43, percentage 3.44, loss due to moisture in fuel 206.91, in percent 5.91, loss due to moisture in air 10.15, in percent 0.29, partial combustion of C to CO 90.32, in percent 2.58, surface heat loss 8.75, in percent 0.25, loss due to unburnt in fly ash 3.85, 0.11%, loss due to unburnt in bottom ash 61.97, 1.77%. Now, the boiler efficiency if we calculate we will get 77.77%. So, the boiler efficiency is 77.77%. Now, the factors affecting boiler performances. The various factors affecting the boiler performance are listed below. Periodical cleaning of boilers, periodical soot blowing, proper water treatment program and blow down control, draft control, excess air control, percentage loading of boiler, steam generation pressure and temperature, boiler insulation, quality of fuel. All these factors individually or combined contribute to the performance of the boiler and reflected either in boiler efficiency or evaporation ratio. Based on the results obtained from the testing, further improvements have to be carried out for maximizing the performance. The test can be repeated after modification or rectification of the problems and compared with standard norms. Energy auditors should carry out this test as a routine manner once in 6 months and report to the management for necessary action. This is the end of today's lecture. Hope we will meet in the next lecture. Thank you so much.